Hello and welcome back. We have understood what is support vector machine and then how it works, how it actually chooses the support vectors so that the margin is maximized. And then we understood the C hyperparameter can be used to play with and find the best model, right? And we have understood that feature scaling is very important for the SVM algorithm to find out best decision boundary or best support vectors. So let us take a data set and try to play with the algorithm and see what we can do with SVM, right? So here I am using linear SVC algorithm. There are two variants of SVC algorithm, SVM algorithm, linear SVC and SVC. Or if you want to do regression, linear SVR or SVR. So both algorithms are dependent on two different libraries. If you want to know the differences, right? The linear SVC will be able to do only linear decision boundaries, but SVC can use kernel trick and do very complex nonlinear decision boundaries. We'll see that in coming sessions. So let us jump in and look at the code first. So here I have taken the iris dataset. The iris dataset is about 3 flowers, 3 different species of flowers. The 3 look similar when you look at them with the naked eye. The 3 look similar, but the sepals and petals lengths and widths are different. So that is the pattern the algorithm need to recognize or understand. Okay, so there is somebody who collected the data. The sepal length, the sepal width, the petal length and petal width, and they flagged it as one of the species, Iris setosa, Virginica or versicolor. These 3 are the names of these 3 species. And if you look at head, it looks like this. And for each class there are 50 records. So the data set is completely balanced, but data set is small. At 150 records we have. Let us see whether we can find a pattern properly or not. So we need to split data into X and Y, right? The input variables and the output variables. The input variables are length, width, petal length and petal width, and the output variable is the species, right? Species is nothing but whether it is setosa or Virginica or versicolor. So we need to split data into train test. The first thing when you are doing any data science project, the first thing you need to do is split data into train test. Then you perform, right? You work with the train set and do all the EDA and all the transformations and build model. Once the model is working good on train set, then you take test set and try to test it whether the model is working good or not. In the process of building train set and testing, you will take cross validation, like k-fold cross validation technique to see whether model will work well on the test set or not. I think you remember all those concepts we covered. If not, right, go back to those sessions and try to recap and come back. So we need to split data into train test. We did that. Train X, test X, train Y and test Y. And we splitted data into 90% and 10%. The test set size is 0.1. That means 10% test set and 90% train set. When you use a train test split, it is going to pull 90% records from this class, 90% records from the second class, and 90% records from the third class, because the train test split method will do a stratified sampling. When I say stratified sampling, it needs a column, it needs a basis to choose that 90%. So here the data set is balanced, but when you split data, the train set and test set should also be balanced. We should make sure that, right? So to make sure that, we can take Y variable as the basis, because Y variable can group records into 50, 50, 50, right? There are 50 records belonging to Virginica, 50 belong to versicolor, 50 belong to setosa. So the Y variable is deciding which group, the record belongs to which group. So you can pick 90% records from each group and make that as train set, 10% records from each group and make that as test set. That activity is done by train test split. It does stratified sampling. That is called as stratified sampling. So we did that, and then we have built a pipeline. We have actually built a pipeline. In the pipeline, the first step is the standard scalar. The second step is the linear SVC. As I said, there are two variants, linear SVC and normal, just SVC. Linear SVC always does linear decision boundaries. SVC can do very complex nonlinear decision boundaries with the help of kernel trick. We'll see that in coming class. So here, the linear SVC I have taken C is equal to 600. So I played with hyperparameter and made the C value too high. Maybe the model is overfitting, right? The model may work well on the train set and may not work well on the test set. So loss function I have taken hinge loss and random state I set 30. Okay, the random state is the the parameter which actually makes the algorithm choose the same random values all the time. Okay, so when you execute the model n number of times, you get the same result. Now I have this pipeline, so I am actually taking the pipeline and fitting the X train and Y train. So when I fit, right, the standard scalar will apply fit and transform both. Right, the pipeline has got that mechanism inside the pipeline. So when you say pipeline.fit, it actually does fit transform on the transformers. These are called as transformers. On the predictors, it will do fit. But when you do predict, right, it will actually call predict method on only those predictors. Not it's not going to touch the transformers. So here, when I did fit, right, it took X and Y. It built a model. It built a model in the sense it found those weights associated with the 4 variables. Here, what are the 4 variables? Sepal length, sepal width, petal length, petal width. It found out the coefficients. Okay. So, and the bias term. And SVM gives you classes also to know the order, right, in which the classes were taken. So, the first class is Iris Satosa, second class is Versicolor, and third class is Virginica. So, we'll see that, what is the use of this, we'll see in a moment. So, I took the train set and trying to make predictions and, evaluate, whether the model is working good or not. To do that, I called the, SVM classifier, the pipeline.predict, and passed xtrain, right? When I passed xtrain, it is going to apply the transformation scaling, and then it is going to make prediction. So standard scalar gets applied automatically, and then it passes the scaled data to model, because while training, when you set fit, right, the same x went into the standard scalar, and the standard scalar actually did the transformation, and then the model got trained, right? So same way here also, when you say predict, the same x train, right, x train is the raw x train here. Whatever data we have, we are passing that raw x train, and it is going to get passed into the standard scalar. As the SVM algorithm is sensitive to scaling, we definitely need to do scaling, feature scaling. I used the standard scalar here. It does the standard scalar, and then the prediction happens. The data gets passed to the model, and it actually predicts. And we have predicted values and actual values. I can do confusion matrix. When you look at this confusion matrix, there are 4400, 0413, and 0143. So let me try to explain what this confusion matrix is. So we have 3 classes, right? Let me take a screenshot. We have 3 classes in our data set: Satosa, Versicolor, and Virginica, right? So when you looked at this confusion matrix, right, this first row, like, let me write this again, right? Let me magnify this. 44 0 0 0 41 3 0 1 46. What are these numbers? We need to understand, right? So the first class is Satosa. When you actually did classifier.classes underscore, it actually is showing you in which order the classes were taken. The order is important to know here, in the confusion matrix it is useful. So Satosa, Versicolor, and Virginica, right? Here also Satosa, Versicolor, and Virginica, right? So on this side, the actual values, right? This is actual. ACTUAR. Okay, this is predicted. The confusion matrix is like that. I hope you remember, right? So These are the classes. So in our data set, in our train set, we have 44 Satosa records. All 44 Satosa records are predicted as Satosa. That's what it is saying. Exactly 100%. No, it was able to identify Satosa. And there are 41 plus 3, right? 41 plus 3, 44 records belonging to versicolor. But the algorithm, the model, the SVM algorithm was able to identify only 41 records correctly. Out of 44 versicolor records, it was able to identify only 41 correctly, and 3 it misclassified as Virginica. Okay, by looking at the confusion matrix, you can understand in between which two classes the model is unable to understand pattern, right? The versicolor and Virginica, it got confused. Same way, the Virginica, there are 47 records in the train set, out of which 46 it was able to predict as Virginica, the predicted actual. But one record it failed to identify it as Virginica and it misclassified as versicolor. So the confusion matrix can be understood on a multi-class classification like this. Knowing the class order is very important to analyze the error and see what we can do more to improve the model, right? Model performance. So that is about the confusion matrix. And you look at the precision score and recall score, 97% we got and train set. If you take test set and try to make prediction, the same model, when I say predict, right, what happens? The test set goes into the standard scaler, the data gets scaled, and then it actually makes predictions. And using those predictions, we did the confusion matrix and precision recall. Now we got 100% precision and recall here because the data set is small. The records chosen may be fitted well, right? The records chosen are actually falling into the pattern the algorithm found, so it is working well. So don't be amazed that the model is not working well on the train set and working well on the test set. These are all two toy data sets and they are very small in size, so sometimes it happens. So that's all about an SVM algorithm, a linear SVM algorithm, linear SVC algorithm, and how to play with it on a data set. And the C hyperparameter, if you play with, right, you can make the model underfitted or overfitted, and you need to find the best place. Always we try to make the model overfitted on train set and adjust it so that the model works well on the train set. Run an extra mile and come back and stay where exact what place you need to stay. So that is how the machine learning algorithm fine tuning happens. Let us meet in another session on how to handle nonlinear data sets using SVM. Thank you.